Welcome to this presentation on designing arithmetic building blocks. My name is Earl Albert, and I'll be guiding you through the important concepts and techniques involved in creating the fundamental components of arithmetic operations. Let's dive in and explore how these building blocks form the basis of more complex computing tasks. On this slide, I'll walk you through the key topics in our syllabus. First, we'll dive into the fundamental building blocks of arithmetic circuits, including data paths, adders, multipliers, and shifters. We'll also explore arithmetic logic units, or ALUs, focusing on their design considerations, especially the trade-offs between power consumption and speed. To give this some real-world context, we'll look at a case study that highlights design as a balance between these factors. Next, we'll shift our attention to memory and array structures. We'll cover the architecture and core building blocks of memory systems, along with the crucial peripheral circuitry that supports them. Understanding these elements is essential for designing efficient and reliable memory components. Together, these topics provide a solid foundation for understanding complex digital systems and the design challenges involved. Here, we're looking at some fundamental components of digital processing. First, the digital processor itself serves as the brain that handles computations and controls operations. Within this, the adder is a critical unit responsible for performing addition, which is a basic yet essential operation in many processing tasks. Moving on, we have more advanced elements like high-speed adders, accumulators, multipliers, and dividers. These components work together to perform complex arithmetic operations quickly and efficiently, which is vital in high-performance computing. Shifters are also key because they enable bit-level manipulations that can speed up calculations by simplifying certain operations. Finally, there's the consideration of speed versus trade-offs. Optimizing for faster processing often involves balancing factors like power consumption and hardware complexity. All of these components come together within the memory architecture and building blocks, creating the memory core that supports the processor's function. Understanding the roles and interactions of these elements is crucial for designing efficient digital processing systems. Here we have the key components of a digital processor. First, the control unit, which directs the operation of the processor by managing how data moves and how instructions are carried out. Next is the data path, where the actual data processing happens through arithmetic and logic operations. Then there's memory, which stores both the instructions and the data needed for processing. Finally, input-output interfaces handle communication between the processor and the external world, allowing data to enter and results to be sent out. Together, these parts work seamlessly to execute complex tasks efficiently. Here we have a bit-sliced data path organization, which is a way of designing the processor's data path by breaking it down into smaller slices, each responsible for processing a specific bit of the data. Here you can see the bits labeled from bit 0 up to bit 3, indicating a 4-bit wide data path. Each slice operates in parallel, working on its respective bit simultaneously, improving efficiency. The control signals manage the operation of these bit slices, ensuring synchronization and coordination. Data comes in through the data in line, flows through each bit slice where it's processed, and then exits via the data out line. This modular approach makes the design scalable and easier to manage, especially for processors handling larger data widths. Now let's talk about VLSI arithmetic units, which are fundamental components in very large-scale integration design. Among these, addition and multiplication stand out as key operations because they're used so frequently in complex circuits. Optimizing these basic units is crucial to improving overall circuit performance. There are two main levels at which this optimization can happen. First, at the logic level, we focus on rearranging Boolean equations to make the circuit faster. This means tweaking the logic itself to reduce delays. Second, at the circuit level, the goal shifts to reducing the physical area the circuit occupies and lowering power consumption. Both levels are essential for creating efficient and effective arithmetic units in VLSI design. The adder is a fundamental component in a processor and it often determines the overall speed of the system because it can be the speed-limiting element. There are several types of adders, each varying in terms of speed and the amount of hardware area they consume. Some common types include the ripple carry adder, which is simple but slower, the carry bypass adder, which improves speed by bypassing some carry operations, the carry select adder, which speeds up addition by preparing multiple carry outcomes in advance, the carry look ahead adder, known for its faster carry calculation, and finally, the tree adder, which uses a hierarchical structure to further optimize speed. Understanding these types helps us balance performance and hardware complexity in processor design. Here, we are looking at the full adder, an essential component in digital circuits used to perform binary addition. The full adder has three inputs, A, B, and CIN, where A and B are the bits to be added, and CIN is the carry-in from the previous stage. The output of the full adder includes sum and COUT. The sum output is calculated using the XOR operation among A, B, and CIN, which is shown as S equals A XOR B XOR CIN. This operation effectively adds the three input bits while accounting for any carry-in. For the carry-out, denoted as COUT, it represents whether a carry is generated from adding these bits. The formula here combines the AND OR operations. COUT equals AB plus B times CIN plus A times CIN. This shows that a carry is produced if at least two of the inputs are high. Understanding these equations is crucial because they demonstrate how the full adder manages both the sum and the carry in multi-bit binary addition, making it a fundamental building block in arithmetic logic units. Here, we're looking at how the sum and carry outputs can be expressed using the generate, propagate, and delete signals. First, generate, denoted as G, is the AND of A and B, meaning it indicates when a carry is definitely produced by these bits. Propagate, or P, is the XOR of A and B, showing whether a carry-in will be passed along. Delete, shown as A and B complement, determines when no carry is generated or propagated. The carry-out COUT is calculated by combining generate and the product of propagate and the carry-in, succinctly expressed as G plus P times CIN. For the sum, it's the XOR of propagate and CIN. Understanding these relationships is crucial for designing efficient adders, since they allow us to predict carry signals quickly and compute sums accurately. Here we have the ripple carry adder, which is a fundamental type of adder used in digital circuits. The key characteristic of this adder is that the carry output from each full adder is passed along to the next full adder in the chain. This means the sum at each stage depends on the carry from the previous stage. You can see the inputs labeled A0 to A3 and B0 to B3, representing the bits we want to add. One important point to note is the propagation delay, which we denote as TD. This delay increases linearly with the number of bits n because each carry has to ripple through every full adder sequentially. The total delay can be expressed as TD equals ON, meaning it grows proportionally with n. More specifically, the formula TATA equals n-1 times the carry delay plus the sum delay shows how the overall timing combines these delays. This ripple effect causes the adder to take longer as more bits are added, which is a limitation when designing faster circuits. Each full adder, shown here as FA blocks, takes the incoming carry and the input bits to produce a sum bit and a carry output that moves to the next stage. The carry out of one full adder becomes the carry in of the next, clearly indicated by the connections labeled CO and CI. Overall, the ripple carry adder is simple and easy to implement, but its linear delay means it's not always the best choice for high-speed operations. Understanding this delay and the sequential carry propagation is crucial when considering trade-offs in adder design. Let's take a closer look at the inversion property. Here, we have elements labeled A and B, along with S, CO, CI, and FA. These terms represent key components or operations related to the property we're discussing. The inversion property essentially tells us how these elements interact or relate when inverted. For example, applying the inversion to element A might result in a transformation involving B or other associated terms like CO and CI, which could stand for specific operations or conditions in this context. Understanding how these elements correspond under inversion gives us a deeper insight into the structure or behavior we're analyzing. It's important to focus on these relationships because they form the foundation for more complex deductions or proofs further along in the topic. Now, let's delve into the circuit design of a full adder. Over time, various logic styles have been developed to implement full adders in an optimized way. These different approaches aim to enhance performance, reduce power consumption, or save area on the chip. Some common logic styles include the static CMOS adder, which is widely used due to its robustness and simplicity. Then we have the mirror adder, known for its symmetrical design and balanced operation. Another approach is the transmission gate-based adder, which uses transmission gates to improve speed and reduce transistor count. Lastly, the Manchester carry chain adder focuses on accelerating the carry propagation to boost overall speed. Each of these designs offers unique benefits depending on the specific requirements of the application. Here we are looking at the static CMOS full adder design, which is implemented using 28 transistors. This circuit is fundamental in digital arithmetic and performs addition of 3 inputs, A, B, and the carry-in, labeled as CI. The full adder outputs a sum, S, and a carryout, COUT. The carryout equation is given by COUT equals AB plus B times CI plus a times CI. This means that if any two of these inputs are high, the carryout will also be high. It ensures proper carry propagation in multi-bit addition. The sum output S is determined by a slightly more complex equation. S equals the product of A, B, and CI plus COUT multiplied by the sum of A, B, and CI. Essentially, this combination of inputs and carry ensures accurate calculation of the sum bit. This design uses complementary MOS transistors to achieve low power consumption and good noise margins, making it reliable and efficient for integration in more complex circuits. The labeling of inputs and power rails, like VDD, highlights the typical CMOS structure, with pull-up and pull-down networks working together to perform the logic functions. Here we're looking at the mirror adder, a fundamental circuit used for binary addition. The key elements include inputs A, B, and the carry-in CI, as well as the power supply VDD. The circuit generates some output S and carry-out company. An important concept here is the way the adder handles the propagate and generate signals. The generate signal indicates when a carry will be produced regardless of the carry-in, while the propagate signals, labeled as 1, propagate, and 0, propagate, determine whether the carry-in will be passed along. This design effectively uses transistor configurations to perform the addition operation. The mirror adder specifically employs 24 transistors to accomplish this, which is relatively efficient. By mirroring parts of the circuit, it maintains balanced paths for signals, improving speed and reducing delay. Understanding how kill, generate, and propagate signals interact within this transistor layout is crucial to grasping the mirror adder's function and performance benefits. Here we have a transmission gate full adder circuit. The main inputs are A, B, and CI, which is the carry-in. These inputs go through transmission gates controlled by signals, such as P and VDD, to generate the sum and carry outputs. The sum generation and carry generation sections are clearly separated, highlighting how the carryout, CO, is formed independently from the sum, S. The use of transmission gates helps reduce transistor count and power consumption, making this design efficient. Understanding this schematic is crucial because it shows how the full adder achieves both sum and carry functions using transmission gate logic. Here, we're looking at the Manchester carry chain adder, which is a key component in high-speed arithmetic circuits. The main idea behind this adder is to efficiently manage the carry signals during addition. You see the variables CI, GI, and pi here. These represent the carry-in, generate, and propagate signals respectively. The generate signal GI indicates whether a particular bit pair will produce a carry regardless of the carry-in, while the propagate signal pi shows if the carry-in will be passed to the next stage. This combination allows the adder to determine carry outputs quickly. Additionally, the inclusion of clock signals represented by phi helps synchronize the operation of the chain. The use of VDD indicates the power supply connections needed for the circuit. Overall, the Manchester carry chain enhances speed by precomputing these carry signals in parallel, reducing the delay that traditionally slows down standard adders. Here we have a 4-bit Manchester carry chain, a key component in digital circuit design for fast addition. The carry chain uses generate signals labeled G0 through G3 and propagate signals P0 through P3, which control how carry bits move through the chain. The carry inputs and outputs, such as CI0 and C0 through C3, show how the carry is passed along each bit stage. Notice the presence of the clock signals indicated by phi, which synchronize the operation. This setup ensures that carries are efficiently generated and propagated, significantly speeding up the addition process compared to ripple carry adders. Understanding how these signals interact is crucial for optimizing arithmetic circuits in hardware design. Here we have the carry bypass adder, also known as the carry skip adder. The main idea behind this design is to speed up the carry propagation through multiple full adders. You can see several full adders aligned, each generating propagate and generate signals labeled P0, G1, P2, G2, and so on. The key concept here is the bypass or skip mechanism. If all propagate signals P0 through P3 are high, it means the carry input can quickly bypass the intermediate stages and directly become the carry output Co3. In other words, when P0, P1, P2, and P3 are all equal to 1, the carry out at the last stage equals the initial carry in CI0. This significantly reduces the delay caused by waiting for the carry to ripple through each full adder. However, if this condition is not met, the adder will either generate or kill the carry internally, ensuring accurate results. The multiplexer plays a crucial role here by selecting whether to bypass the carry or to use the generated carry based on these propagate signals. So, the carry skip approach improves speed by allowing the carry to skip over blocks of bits when possible, rather than waiting for a ripple effect through every bit, making it a clever compromise between complexity and performance. Here, we're looking at a 16-bit carry bypass adder and analyzing the timing aspects involved in its operation. The key components affecting the overall delay are the carry propagation, setup time, and sum generation. The adder is divided into smaller blocks, each handling m bits. For example, bits 0 to 3 form one block, bits 4 to 7 another, and so on up to bit 15. Within each block, the carry must propagate through the bits, which takes a certain amount of time, represented here as tkari. Each bit also requires a setup time before the sum can be computed. The bypass logic helps speed up the carry propagation between blocks, allowing the carry to skip over entire blocks if possible, reducing the delay. This bypass time is denoted as bypass. To calculate the total delay of the adder, we sum these components: the setup time, the sum computation time, the carry propagation delay through m bits, the bypass delay times the number of blocks minus 1, and finally, the carry propagation time within each block minus 1 bit. Understanding this formula and the breakdown of delays helps optimize the design of the carry bypass adder to achieve faster addition speeds by balancing block sizes and bypass logic efficiency. Here, we're comparing the carry ripple adder with the carry bypass adder. The ripple carry adder is straightforward, but can be slower because each bit must wait for the previous carry to propagate through, resulting in a delay proportional to n, the number of bits. On the other hand, the carry bypass adder improves speed by allowing certain groups of bits, typically between 4 and 8, to bypass waiting for carries to propagate through every single bit. This means the bypass order effectively reduces the propagation delay. However, despite this improvement, the ripple carry adder is often considered the best choice for simpler or smaller designs due to its simplicity. So, while the carry bypass adder offers better performance in some cases, the ripple carry adder remains a solid and widely used option. Now let's take a closer look at the carry select adder, which is designed to speed up the addition process by handling carry propagation more efficiently. The key idea here is to prepare for both possible carry inputs, 0 and 1, simultaneously. The setup involves generating two sets of sums and carry outputs, one assuming the incoming carry is 0, and the other assuming it is 1. This way, we don't have to wait for the actual carry to propagate through all bits sequentially. The multiplexer plays a crucial role by selecting the correct sum and carry outputs based on the actual carry input. This approach reduces the delay that typically occurs during carry propagation. You can see the terms co, k, 1, and co, k plus 3 representing carry outputs at different stages, while the values 0 and 1 correspond to the two carry propagation scenarios processed in parallel. Lastly, the sum generation and the carry vector depend on the propagate and generate signals, noted here as P and G, which help determine how the carry is managed throughout the addition process. Overall, the carry select adder effectively balances complexity and speed, making it faster than a simple ripple carry adder by working on multiple carry assumptions in parallel. Here we're focusing on the critical path of the carry select adder. The design divides the addition process into different groups of bits: bits 0 to 3, 4 to 7, 8 to 11, and 12 to 15. Within each group, sum generation happens for both possible carry inputs, 0 and 1, simultaneously. This means that for each group, we prepare two possible sums, one assuming the carry-in is 0, and the other assuming it is 1. After sum generation, a multiplexer selects the correct sum based on the actual carry coming from the previous group. This selection process is crucial because it determines the correct output sum for those bits. The carry outputs, labeled co for bits 3, 7, 11, and 15, represent the carry output for each group. The initial carry input is CI 0, starting the chain. The critical path here is influenced by the time it takes for sum generation and the multiplexer selection in each group. Since sum generation is done in parallel for both carry inputs, the multiplexer introduces the main delay in determining the actual sum and carry output. Therefore, understanding this process helps in optimizing the overall speed of the carry select adder, as we can focus on minimizing the delay caused by multiplexers and efficiently managing carry propagation between groups. Here, we're looking at the linear carry select adder architecture. The key idea behind this design is that it divides the adder into smaller blocks, each responsible for a group of bits. In this case, bits 0 to 3, 4 to 7, 8 to 11, and 12 to 15. Each block prepares two sets of sums and carry outputs in parallel, one assuming the carry input is 0, and the other assuming it's 1. This is shown here with the separate 0 carry and 1 carry paths. A multiplexer then selects the correct sum and carry based on the actual carry from the previous block. This setup allows the adder to reduce the delay caused by waiting for the carry to propagate through each bit individually. Instead of waiting, each block gets ready for both possibilities simultaneously, and once the correct carry is known, it quickly selects the right output. The sum generation blocks produce final sum bits, indicated as S0-3, S4-7, S8-11, and S12-15. The carry inputs and outputs are carefully managed to ensure seamless operation across the different stages. Overall, this approach balances complexity and speed, making it faster than a simple ripple carry adder, while being more straightforward than some other high-speed adders. Here we're looking at the square root carry select architecture. The basic idea is to improve speed by preparing two sets of sums simultaneously, one assuming a carry-in of 0, and the other assuming a carry-in of 1. For each group of bits, you see two parallel setups. One calculates the sum and carry with a 0 carry-in, and the other does the same with a 1 carry-in. Then, a multiplexer selects the correct output based on the actual carry from the previous group. This eliminates the delay associated with waiting for the carry to propagate through each bit sequentially. Looking at the bit groupings, we process bits 0 through 1 first, then bits 2 to 4, 5 to 8, 9 to 13, and finally bits 14 to 19. Each group has its own pair of carry setups and multiplexers. The sums generated from each section are then combined to produce the final result. This approach significantly reduces the overall delay compared to simpler designs because the time-consuming carry calculations happen in parallel rather than serially. The multiplexers efficiently pick the correct sum based on the actual carry, enabling faster arithmetic operations. Overall, the square root carry select method strikes a good balance between complexity and speed, making it a popular choice in arithmetic circuits. Here, we are comparing the delays associated with different types of adders. The main focus is on how the delay scales as the number of bits, represented by n, increases. For a 25-bit adder, we see three different approaches: the ripple adder, the linear select, and the square root select. Starting with the ripple adder, its delay increases linearly with n, meaning that the delay is proportional to the number of bits. This leads to longer delay times as the bit width grows. Next, the linear select adder improves on this by reducing the delay somewhat, but it still increases noticeably with n. Its delay values are found between the ripple adder and the square root select. Finally, the square root select adder shows the best performance here. Its delay increases much more slowly compared to the other two, roughly following the square root of n. That means for larger bit widths, this design offers significantly faster operation. Overall, this comparison highlights the importance of choosing the right adder architecture to balance speed and complexity depending on the application requirements. The square root select adder offers a more efficient way of handling delays in wide adders. Here we're looking at the concept of look-ahead topology in carry computation. The key idea is to determine the carry output more efficiently by expanding the look-ahead equations. Starting from the basic equation, k is expressed as gk plus pk times the carry from two stages before k2. This recursive approach reduces the time it takes to propagate the carry through multiple stages. We see in the detailed equations how each carry output, from C0 up to C3, is computed. For example, C0 depends on G0 and P0 times the initial carry-in, CIN. C1 builds on this by including terms from G1 and P1 multiplied by previous generate and propagate signals, reflecting the dependency across different bits. The expansion continues with C2 and C3, incorporating more terms that account for all previous bits generate and propagate signals. Notice how each term captures the cumulative effect of these signals on the carry generation. This method allows us to quickly compute the propagating carries without waiting for serial propagation, which is crucial for improving the speed of arithmetic circuits. The notation here ties back to the basic building blocks, G and P, which represent generate and propagate signals, respectively. Understanding these equations is fundamental to grasping how look-ahead adders accelerate addition by reducing carry delay through parallelization of carry calculations. Here, we're looking at a 16-bit radix, 2-Kagistone tree, which is a type of tree adder used for fast binary addition. Each pair from A0, B0 up to A15, B15 represents the bits of the two numbers being added together. The Kagistone tree efficiently calculates the carry signals across all bits in parallel, which allows for very fast addition compared to simpler ripple carry adders. The outputs S0 through S15 are the sum bits resulting from this addition. This structure is known for its speed and is widely used in high-performance arithmetic circuits because it reduces the overall propagation delay by generating carries in a logarithmic number of stages. Now, let's discuss multipliers. Multipliers are powerful tools or factors that can significantly amplify outcomes or effects in various contexts. Understanding how they work is crucial because they help us recognize opportunities to maximize impact, whether in finance, economics, or business strategies. The concept revolves around how an initial change can lead to a larger overall result, making it important to identify and leverage these multipliers effectively. Here, we're looking at the concept of binary multiplication, which is fundamental for digital systems and computing. Essentially, when we multiply two binary numbers, x and y, we denote the product as z. This product can be expressed as a summation, where each term represents a weighted contribution from the bits of x and y. X is represented as a sum from I equals 0 to n minus 1, where each bit x sub I is multiplied by 2 raised to the power of I. Similarly, y is expressed as a sum from j equals 0 to m minus 1, with each bit y sub j weighted by 2 to the j. When we multiply x and y, the product z is the sum over k from 0 to m plus n minus 1 of the binary value z sub k multiplied by 2 to the k. This structure highlights the way each bit of x interacts with each bit of y, and the indices I and j combine to form the index k in the product. Understanding this summation and indexing helps in designing efficient hardware multipliers and understanding how binary multiplication works at a fundamental level. Here, we're looking at binary multiplication, which works similarly to decimal multiplication but uses only zeros and ones. The multiplicand is the number we're multiplying, and the multiplier is the number we multiply by. For each digit in the multiplier, we create a partial product. When the multiplier digit is 0, the partial product is all zeros. When it's 1, the partial product is just the multiplicand shifted according to the position of that digit. After calculating all the partial products, we add them up to get the final result. As you can see in this example, the binary numbers multiply to give the combined product shown at the bottom. Understanding this process is essential because it forms the basis for many computing operations at the hardware level. Here, we have the structure of an array multiplier, which is a hardware circuit used for multiplying binary numbers efficiently. The inputs are represented by x and y values, where x3 to x0 and y3 to y0 correspond to the bits of the two binary numbers being multiplied. The multiplier operates by generating partial products for each combination of bits from x and y, and then these partial products are added together using half adders, HA, and full adders, FA. These adders help to sum up the intermediate results and manage the carry bits properly. The outputs, labeled as Z0 to Z7, represent the final product bits of the multiplication. The array layout allows simultaneous processing of multiple partial products, resulting in a faster multiplication operation compared to sequential methods. Understanding the role of each adder and how the bits are combined is key to grasping how the array multiplier achieves this parallel processing. Here, we are focusing on the carry-save multiplier, which is a crucial component in high-speed arithmetic circuits. The key idea behind the carry-save approach is to manage the addition of multiple binary numbers efficiently by reducing the propagation delay associated with carry bits. You can see several instances labeled as HA and FA, representing half adders and full adders respectively. These adders form the fundamental units of the multiplier. Half adders handle the addition of 2 bits, while full adders manage the addition of 3 bits, including the carry from previous stages. The arrangement of these adders allows partial products to be summed quickly without waiting for carry propagation in every step. This is what gives the carry-save multiplier its speed advantage over traditional multiplication methods. Finally, the vector merging adder at the end combines the partial sums and carries generated by the previous stages into a final product. Altogether, this structure allows the multiplier to perform fast and efficient binary multiplication, which is essential in many digital signal processing and computational tasks. Here we have the multiplier floor plan, which visually breaks down how the multiplier is structured at the cellular level. You can see the array consisting primarily of C and S cells. These represent the core computational units, where C typically stands for carry cells and S for sum cells. The signals labeled X and Y are broadcasted throughout the entire array, allowing all cells to receive the necessary inputs simultaneously. At the intersections of these signals, the HA and FA multiplier cells, half adder and full adder cells, respectively, handle the bitwise addition required in multiplication. The vector merging cells play a crucial role in combining intermediate results as we move through the stages. On the output side, signals Z0 through Z7 represent the final product bits after all summations and carry propagations within the array. This layout helps us understand how the multiplier efficiently processes inputs in parallel, achieving fast and accurate multiplication results. Here we're looking at the Wallis-Tree multiplier, a method used to speed up the process of multiplying binary numbers. The first stage involves generating partial products, which are essentially the initial results from multiplying bits of the numbers. You can see these partial products aligned according to their bit positions, which range from 0 up to 6 here. Moving on to the second stage, the partial products are combined using a series of full adders and half adders, abbreviated as FA and HA on the slide. This stage reduces the number of partial product rows by summing bits that align in the same bit positions. The goal is to minimize the number of subsequent addition operations. Finally, after these reductions, the output is fed into a final adder. This step completes the multiplication by adding the remaining sums and carries, resulting in the final product. The labels A, B, C, and D correspond to different parts or steps in this process, illustrating how the Wallace tree efficiently consolidates the partial products into the final result. This structure is crucial because it significantly speeds up binary multiplication compared to more straightforward methods. Here, we're focusing on the Wallace tree multiplier. This is a hardware implementation technique used to multiply two numbers efficiently. The key idea behind the Wallace tree is to reduce the number of partial product rows quickly by using a tree of carry-save adders, which significantly speeds up the multiplication process compared to traditional methods. By organizing the partial products into layers and combining them strategically, the Wallace tree reduces the overall computation time. This makes it very effective in high-speed arithmetic circuits, especially in digital signal processing and other applications requiring fast multiplication. Understanding this multiplier helps us appreciate how hardware can optimize complex operations. Now let's talk about shifters. Shifters are words that change their meaning depending on the context in which they are used. Unlike regular words that maintain a consistent meaning, shifters are highly context-dependent. This means their interpretation can shift based on who is speaking, when, or where. For example, words like I, here, and now are classic examples of shifters because their reference changes depending on the situation. Understanding shifters is crucial because it helps us grasp how language functions dynamically in real communication, connecting language directly to the context. This concept underlines how meaning is not fixed but can vary, which is essential when studying language, and how we convey information effectively. Here, we're looking at the concept of a binary shifter, which plays a critical role in manipulating binary data. Notice the bits labeled AI and AI1, as well as BY and BY1, representing the current and previous bits in the sequence. The shifter can move these bits to the right or to the left, as indicated by the arrows. The term NOP, under left, suggests a no operation, or that the shift might not occur in that direction under certain conditions. The term bit slice I indicates that this operation applies specifically to the ith bit slice, implying that the shifter processes data one slice at a time. Understanding how these bits move and interact is fundamental for grasping how shifts affect binary values in computing processes. Here we're looking at the barrel shifter, which is a crucial component for quickly shifting data bits within a processor. The labels 0 shillings through 3 shillings represent the control wires that determine the amount of shifting we apply. These control signals guide the barrel shifter to rotate or shift the input bits, labeled from A0 to A3 and B0 to B3, to the desired position. The data wires carry the actual bits that are being shifted. This arrangement allows for efficient manipulation of data without the need for multiple clock cycles, enhancing processing speed. Understanding how these control and data wires interact is key to grasping the barrel shifter's role in rapid data handling. Here, we're looking at the concept of a logarithmic shifter. This type of shifter works by shifting bits in powers of 2, rather than one position at a time. The labels 1 shilling, 2 shillings, and 4 shillings represent shifts by 1, 2, and 4-bit positions respectively, allowing for quick and efficient bit manipulation. The input bits labeled A0 through A3 and B0 through B3 correspond to the data inputs and control signals that determine how the shifting occurs. By combining these shifts, the logarithmic shifter can move bits across multiple positions in just a few steps, which is much faster than simple linear shifting. This mechanism is crucial in applications requiring rapid data processing and efficient hardware design. It looks like this slide is blank or doesn't have any content. Could you please provide the specific text or points you'd like me to narrate? That way, I can help you craft a clear and engaging script. It seems this slide doesn't have any content on it. If there's a specific topic or point you want to discuss here, please let me know so I can help you craft the perfect narration. It seems like this slide is blank or missing content. Could you please provide the text or main points included on this slide? That way, I can help you create an effective narration script. It seems this slide is currently blank or missing content. Could you please provide the details or key points that should be covered here? That way, I can help create a clear and engaging narration script for you. It seems like this slide doesn't have any visible content or text, so I'll need a bit more information to provide a detailed narration. If you could share the main points or the topic of this slide, I'll be happy to help craft a clear and engaging script for you. It looks like this slide doesn't have any specific content listed. Could you please provide the text or main points that are on this slide? That way, I can help craft the narration script for you. It looks like this slide doesn't contain any specific content or key points to discuss. If you have any particular information or topics you want me to cover here, please let me know. Otherwise, we can move on to the next slide or focus on the main ideas you want to highlight. It looks like this slide is empty or there's no content displayed here. Could you please provide the text or main points you want me to cover? That way, I can help you craft the narration script effectively. I see that this slide is currently blank. Could you please provide the text or main points you want to cover here? That way, I can help you create an engaging and clear narration script. It seems like this slide is blank or doesn't contain any content. Could you please provide the text or main points from this slide so I can help you with the narration? It seems like this slide is currently blank or missing content. If you could provide the details or key points you want to cover on this slide, I'd be happy to help you create a clear and engaging narration for it. It looks like this slide is blank or doesn't contain any content to discuss. Could you please provide more details or check if there's any text or points you'd like me to cover here? It seems this slide doesn't have any specific content to discuss. If there's any information or key points you'd like me to cover from this part of the presentation, please let me know, and I'll be happy to explain them in detail. It seems this slide is blank and doesn't contain any content to discuss. If you'd like, I can help you prepare narration for other slides or assist with adding content to this one. Just let me know. It seems there's no specific content on this slide to talk about. Could you please provide the text or main points from the slide so I can help you with the narration? It seems this slide is blank or does not contain any text or visual content. If there is something specific you'd like me to discuss or explain related to this slide, please let me know. Otherwise, we can move on to the next slide where the content is available. It looks like this slide doesn't have any visible content or key points to discuss. If you could provide more details or specific information that should be covered here, I'd be happy to help you craft the narration. It looks like this slide might be missing some content or details. Could you please provide the text or main points that should be covered on this slide? That way, I can help create an effective narration for you. It looks like this slide is currently empty or doesn't contain any content. Could you please provide the specific text or key points you'd like me to cover for this slide? That way, I can create a detailed and engaging narration for you. It looks like this slide doesn't have any content to discuss. If there's anything specific you want to add or any topic you want me to cover here, just let me know. Otherwise, we can move on to the next slide. It seems this slide doesn't contain any visible text or images, so I'll focus on summarizing the main ideas we've covered so far and how they connect to our next steps. If you have any questions or want me to elaborate on specific topics, feel free to ask at any time. Otherwise, let's keep moving forward to dive deeper into the details and ensure we have a clear understanding of the key concepts. It looks like this slide doesn't have any visible content for me to explain. Could you please provide the text or main points from this slide so I can help you with the narration? It looks like this slide is currently blank or doesn't contain any content. If you have any specific points you'd like to discuss, or if there's information missing that should be included here, please let me know. Otherwise, we can move on to the next slide. It looks like this slide is blank or contains no visible content. Since there's nothing presented here, I'll pause to see if there's another slide or topic you'd like me to focus on. Just let me know how you'd like to proceed. It seems like this slide doesn't have any visible content for us to discuss. If there's specific information or topics you want me to cover here, please let me know so I can provide the right narration. Otherwise, we can move on to the next slide with more details to explore. It looks like this slide doesn't have any visible content or text for us to discuss. If there's a specific topic or data you'd like me to cover here, please let me know so I can walk you through the key points clearly and effectively. Otherwise, we might want to check if there was supposed to be any information on this slide before moving forward. It looks like this slide is empty or the content didn't come through. Could you please provide the text or details from the slide so I can help with the narration? It seems this slide doesn't contain any visible content or key points to discuss. If there is specific information associated with this slide, please share it so I can provide a detailed and engaging explanation. Otherwise, we can move on to the next slide where we have more details to explore. It seems this slide doesn't contain any visible content or text for me to explain. Could you please provide the details or key points that should be covered on this slide? That way, I can help craft an effective narration for you. It looks like this slide doesn't contain any visible text or images. Could you please provide the specific content or the key points you'd like me to narrate? That way, I can create an effective and engaging narration for you. It seems there is no specific content on this slide. If this is a blank or transition slide, I'll pause here and wait for the next slide or any additional information you'd like me to cover. Please let me know how you'd like to proceed. It seems like this slide is empty or doesn't contain any visible content. If you'd like, I can help you craft a narration to wrap up your presentation or transition to the next topic. Just let me know how you'd like to proceed. It looks like this slide is blank or missing content. Could you please provide the text or main points that should be on this slide? That way, I can help you with the narration script. It looks like this slide is blank or doesn't contain any visible content. Could you please provide the text or main points you'd like me to cover? That way, I can create a clear and engaging narration for you. It looks like the slide appears to be blank or doesn't contain any visible content or text. Could you please provide more details or clarify what specific information or topic this slide covers? This will help me create an effective narration script for you. Since this slide appears blank or contains no visible content, I'll use this moment to emphasize any final thoughts or key takeaways from the presentation. This is a great opportunity to remind everyone about the most important points we've discussed, answer any lingering questions, or highlight next steps. If there's anything specific you'd like me to walk through again or any topics to clarify, please feel free to let me know. Otherwise, we're nearly at the end, and I appreciate your attention throughout. On this final slide, I want to emphasize the key takeaways we've covered. It's important to remember the core concepts we discussed and how they interconnect. Think about how these ideas apply to your own work or study, and how you can use them moving forward. If you have any questions or need clarification on any points, now is a great time to bring them up. Thank you for your attention throughout this presentation. As we wrap up, I want to emphasize the key takeaways from our discussion. Remember, the strategies we've covered are designed to help you improve efficiency and achieve your goals more effectively. Focus on implementing these practical steps, stay adaptable, and continuously seek feedback to refine your approach. By doing this, you'll be well positioned for success in your projects and initiatives. Thank you for your attention, and I'm happy to answer any questions you may have.